Okay, good morning, everyone, and welcome to this very special ICTS distinguished lecture, for which we are thrilled to have Professor Sanjeev Arora from Princeton. Before I introduce him, I wanted to welcome most of you to ICTS. Perhaps many of you are here for the first time. I saw that we had a very enthusiastic turnout to our registration page, and a lot of people from industry and people from academia, of course, but perhaps for coming here for the first time. So I thought I'll just give you a very quick bird's eye view of what ICTS is and the kind of unique institution that we are in the Indian scientific context. So ICTS's mandate is sort of threefold. We have our own in-house research in a number of areas in theoretical physics and mathematics, quantitative biology, and going ahead, theoretical computer science, hopefully. But in addition to our research, we have programs. We have special collaborative workshops. We have discussion meetings. We have schools, which are in a number of areas, and not just those in which our faculty conduct research in. In fact, the programs is an open submission through an open submission process, and people from the scientific community anywhere in the world are more than welcome to put their proposals to organize an activity at ICTS. And finally, both of these are closely integrated with our outreach activities as well. And many of you may have seen some of the, if you're from Bangalore, perhaps you've heard of our Kaapi with Kuriosity and various other public lecture events that we have. As an institution, we sort of modeled after several peer institutions elsewhere in the world, like the KITP in Santa Barbara, or MSRI in Berkeley, Newton Institute, or the IAS Princeton, or ICTP Trieste. But in some ways with significant innovations, which makes ICTS sort of a one-of-its-kind institution. And in this sense, I think it holds out immense possibilities for Indian science. So this is what the campus, so we are a new institution. This is what the architects planned in 2012, and very soon, by 2015, much of this was up from the ground, and we moved in 2015 after some final sort of the final dotting of the I's and crossing of the T's. We sort of by 2017, we were in the final state that you see now. So this is just the buildings. If you have a chance, walk around our campus and take a look at our library, for instance. It has a nice design. We have a major computing center because, and since this might be of interest, since many of you are from a computing background, we have people here who were involved in the LIGO discovery of gravitational waves, and a lot of the computing that went into some of the determination of some of the parameters of the black holes that merged happened with some of the high performance computing that we have here. So in terms of our research, we have a young faculty, a youthful faculty in a number of areas. Our faculty, we don't have any departments as such. We believe in having people with very strong core strengths, but an intellectual curiosity that spans disciplines. At the moment, we have something like 8 regular faculty and about 5 visiting joint faculty. And these are some of the areas that are covered. In mathematics, we have dynamical systems, PDEs, big data, geometry and mathematical physics. We've just grown a group in probability theory. as I mentioned, the LIGO discovery by our astrophysics group. And we have a large complex systems group which spans areas in statistical physics, both classical and quantum statistical physics, condensed matter physics, fluid dynamics, and quantitative biology. And finally, in string theory, quantum field theory, and quantum aspects of gravity. So the ICTS programs that I mentioned have a unique, they are not conferences or, I try to emphasize that ICTS is not a conference center or a funding node, but rather we function as a hub for the science community. So in that sense, we are a national facility which can bring together scientists and in some ways catalyze transformations in Indian science as a whole. And we do this through these programs which are unique in their format, in their duration, and organization and directions. I'll just briefly say a bit about each of them. The format is unique in the sense that there's often a strong pedagogical component, and some of our activities are purely schools. And we try to bring in the top experts in a discipline to try to transfer expertise to younger researchers, especially those who wish to enter a new area. And then we archive these lectures on our YouTube channel, which if you haven't seen it, do take a look at ICTS Talks. I think we have about 16,000 subscribers now. And if I'm not mistaken, we just overtook the Institute for Advanced Study in at least the number of our YouTube subscribers. So in that sense, we are creating a certain knowledge capital in the country, and it's in many ways more cost effective than sending Indians abroad to schools. So the duration of these programs is also, again, can go from 2 weeks to 2 months. We had a month-long cosmology meeting and a large one on probability theory just recently. We've had things almost a semester long as well. So that it gives opportunity for researchers from around the world to come and spend long periods together and work collaboratively, and also the younger people to closely interact by being a residential campus. Program participants are housed here, and they get a chance to immerse themselves with fellow participants in their discipline. And I think this can help. It's already helped and can and will go on to help in integrating India more effectively with global science. We are also a node for various institutional cooperation with a lot of international entities and a lot of joint programs with several institutions. As I said, the program submission system is an open one. It's vetted by a program committee, and actively shaped in many ways by the program committee. So we try to, the program committee can suggest new topics and broaden the scope or integrate it with other programs and use the memory of past programs to sort of create an effective program. And we encourage our organizers to form a long-term association and remain engaged with ICTS. So in that sense, it's different from a conference center where people just sort of helicopter in and go out. We are sort of actively involved here in shaping the programs and keeping a certain historical memory of that. And especially in terms of the directions, we try to encourage new initiatives and directions. And this machine learning initiative that we embarked on is one such. But we want to basically get the Indian community to sort of get up to speed in some area. We try to do it in a sustained way through a number of activities. And in machine learning, we had already now a couple of discussion meetings. In 2017, we had something which brought together physicists and computer scientists, neuroscientists. And then a few months ago, some of you may have been here for another meeting on the theoretical basis of machine learning. And tomorrow's set of lectures by Sanjeev is sort of part of that initiative. And going ahead, we plan to have many more, including schools, a regular machine learning seminar, and eventually long collaborative programs. And it's meant to, in fact, connect some of these activities, and like this one, are meant to connect scientists and engineers and industry, sort of that whole pipeline, and let knowledge sort of freely transmit across this, because that's often what is lacking in India. Our academic institutions are often sort of sequestered from the industry, and there's very little communication, which in areas like machine learning, and I'm sure we'll hear, there's a lot of back and forth. A lot of the interesting questions are motivated from the applications or things you would like to do. Maybe people in various areas or different environments, and I'm sure India will have its own set of questions that will come up in applying machine learning to questions of relevance to Indian society. You need to have this communication of between academia and industry, and we hope to strengthen that chain over here through meetings like this. So in terms of numbers, we've had more than now about 2,000 participants come through every year. Last year, we had about 30 programs and about 400 participants from outside India in the last year alone, but cumulatively, these are some of the numbers. We've had over 140 programs and 60 plus discussion meetings, including some of our named lecture series. And distinguished lectures like this one. Sanjeev, in fact, gave one of the inaugural Turing lectures, which is in computer science and biology. Our calendar, if you look up on our webpage, is filled with events. So if you would like to, you can subscribe, subscribe to our newsletter and to our calendar, and stay abreast of the lectures and events that are held here. In addition to the programs, there are a number of public talks and so on. So I encourage you to look at this. But you can see that the calendar is completely full, and that's an indication of the demand for a place like ICTS, the kind of programs we hold. And this is just a sampling of the areas which go from biology, physics, and mathematics, all the way from small scales to very large scales, etc. Finally, just about our outreach, we take it very seriously. We have had a number of public lectures by galaxy of eminent scientists. You may have heard recently some of the talks in cosmology that we had. As I said, we've been very popular and active on social media as well. We've had some special initiatives like the 100 years of general relativity and the mathematics of planet Earth, etc. Kaapi with Kuriosity is our sort of flagship outreach event, which we are holding with the Bangalore Planetarium, and has a talk come discussion format. And once again, I think the number of school college students who've been coming has been very heartening, and it's running for now more than 2 years, and doing very well. We just had one this last Sunday on Ramanujan's mathematics, so it's held on a Sunday afternoon in the planetarium every month. So just again, look at our webpage for the upcoming talks. And this is just a sampling of the various Kaapi with Kuriosity talks we've had. So for our 10th anniversary last year, we had a very special set of events, including the ICTS at 10, for which Sanjeev had also come, and a panel discussion on the usefulness of useless knowledge, and finally a Big Bang kind of event, the public lecture by Kip Thorne, which was like a rock concert. If you haven't seen it, do look at the YouTube video. It's even if you are not so interested in gravitational waves, I'm sure you'll find this captivating. Okay, that's it from my side. And so thank you very much. Let me just go on to actually introduce Sanjeev. Sanjeev is, of course, a very distinguished computer scientist. He is the Charles Fitzmaurice Professor of Computer Science at Princeton, and currently also a visiting professor at the Institute for Advanced Study at Princeton, and in particular helping to run a special program on machine learning, a special initiative on machine learning. And he did his bachelor's at MIT and then his PhD at the University of California, Berkeley. He's known for some of his seminal results on probabilistically checkable proofs, the PCP theorem, and other works on computational complexity, including approximating NP-hard problems. But recently he's been interested and runs a very active group on machine learning between the university and the institute. He has received a number of awards and recognitions. These include the Packard Fellowship, 97, the Simons Investigator Award. He's a twice recipient of the Gödel Prize in 2001 and 2010, the ACM Prize in Computing in 2012, and the Fulkerson Prize in Discrete Maths in 2012 again. And finally, he's a fellow of the American Academy of Arts and Sciences, as well as of the National Academy of Sciences. So it's with great pleasure that I welcome Sanjeev and to give a series of lectures, starting with the one on the mathematics of machine learning.
Well, thanks for the warm welcome. So this is an introductory talk on machine learning and deep learning, where I try to give you a fairly non-technical introduction to what machine learning is, and at the same time, towards the end, give you a taste of some of the research questions and what we're doing. And the other two lectures will give more details about the research. So machine learning, I think of as a new kind of science. So of course, you've all seen it in newspapers and magazines. Because of machine learning these days, machines can understand images in many domains better than humans, superhuman capabilities. They can translate between languages, basically at close to human abilities, and approaching that ability in self-driving cars, etc. Okay, so you've seen the technological aspect of the field in these news reports. And formally, it's also a new kind of science. It's a science of creating machines or programs that improve from experience and interaction. So that's what learning is. And the older term artificial intelligence is not favored as much in the last 10, 15 years because imitating human intelligence is not an explicit goal. Initially, it was just because it was just too embarrassing. The machines were too weak compared to humans. These days, they are approaching or exceeding human capabilities in many domains, but in other domains, they're not as good. And we'll discuss more later that maybe that's an inherent situation for the foreseeable future. All right, so this field forces us to formulate what is learning. The naive sort of questions. What is learning? What does it mean to understand the world? For example, an image is a sequence of pixels. What makes a sequence of pixels correspond to a scene with a pedestrian? Something that you hope that your self-driving car will be able to solve. So these are kind of naive questions, or naive-looking questions, and to make them precise and mathematical is the challenge in this field. And you can think of these as very simplistic questions along the lines of Isaac Newton sitting under his apple tree and asking, what makes the apple fall down to the earth? And it's kind of naive because for thousands of years, of course, people had seen the apple fall, and it never occurred to them that there's a question there. And it's sort of similar over here. So the overview of the rest of the talk, I'll give you a mathematical formulation, but don't be afraid. It's very non-mathematical, actually. Very little math is needed. And give you some examples of machine learning in action. Some buzzwords here are unsupervised learning, sequential decision-making, etc. Then I'll give you just a very brief introduction of the kinds of research my group is interested in, which is mathematical understanding of deep learning, which is an important kind of machine learning today. And then the last part is taking stock and some concluding thoughts. So it's a tour with many stops. And so it's okay if you don't understand a particular slide. Very likely you'll catch up in a slide or two again. So part one, mathematical formulation of machine learning. And I encourage your questions, by the way. I'll periodically stop, and please don't hesitate to ask questions. So operationally speaking, machine learning has a very simple idea. It boils down to learning patterns in data. What does that mean? Maybe you've heard that term, that it's learning patterns in data. But what does that mean? What it means mathematically is something very simple that you've seen since high school, curve fitting. So fitting a curve to experimental data. And the mathematics for this actually goes back at least a couple of centuries to people like Legendre and Gauss. So here's an example. So this is a scatter plot of inflation and unemployment figures from Japan during a certain period. So you look at these inflation and unemployment points, and you squint at it and you say, well, it's sort of like a straight line. And so that's a straight line that you might draw to fit these points. So that's indeed called the Phillips curve in economics. Okay, so that's a very simple curve that you fitted to this data. So now you may remember that you did this in high school science. Here's another example from high school science, the gas law, which connects the pressure, volume, temperature, and mass of a piece of gas. And that was also discovered by fitting this surface, PV equals nRT, to the experimental data. And of course, later, this law was mathematically explained from statistical physics. But initially, it was just an experimental law. So machine learning is similar. It's also using surface fitting, more complicated surfaces, not these simple surfaces, to many more variables, tens of millions of variables, even today, billions of variables. So these are massive models, which are fitted to a lot of data. And when you fit this surface, you learn the pattern in data. So for instance, here, the pattern you learn is this linear relationship, or approximate linear relationship between inflation and employment, and this is the gas law. So these are the patterns in data, which allows you to predict new things. So here's an example, very simple example. This is kind of the example that we use in first week of undergrad machine learning. So learning to score movie reviews, assign a numerical score to a movie review. And the numerical score is from -3 to +3. So here's an example. So this is the movie La La Land. I took this review from Amazon. Slow moving, couldn't get into this movie despite all the awards it has won. So by reading this, these couple of lines, a human rater might say, on the scale of -3 to +3, it rates -1.5. It's sort of negative. Okay, here's another one. Wow, did not know what to expect and was delighted. Loved the homage paid to the musicals of old. So here a human rater might give it a score of 2.5. It's very positive. So the task is going to be, you're given a bunch of reviews and their numerical scores assigned by humans. And your task is to learn to predict the rating score given the text of a new review, one you haven't seen before. So this is the task for the machine. Okay, so it's given a data set of reviews and ratings, and then from that, it's supposed to learn to predict scores of new reviews. So given our discussion of laws and gas laws and so on, you may now be wondering, what is the law of movie review scores? Well, reality is complicated, and probably there's no simple law for this. Okay, so we are really going to try to get an approximate law. And the simplest approximate law is what's called the linear model. So this law, the simple linear model, hypothesizes that for each of the words in the English dictionary, so that's about, let's say, 100,000 words, give or take, for each word in the English dictionary, the human rater has a score, a numerical score, a sentiment score for every word. So for each of the 100,000 words, your brain has a numerical score, which is a scalar. So theta sub W is the score for W, word W. And the model is that the review score, so when you see a review, the score, the numerical score you come up with is just the average score of all the words in the review. Okay, scaled appropriately. So this is called the linear model. So now, if a machine is trying to imitate the human, well, it doesn't know this scalar in your head for each word, it's going to try to learn it from data. So it has a variable for each of these 100,000 words, this theta sub W variable, and it's going to use the data set of reviews and scores to do surface fitting for these 100,000 variables. So how does that work? Well, so the variables are theta sub W, one for every word in English, and the machine has given a bunch of examples, the data set of reviews and scores. And so for each review, it computes the sum of the scores for the words in the review and matches it to the humanly assigned score. And I'm ignoring here for simplicity the scaling. So this is called the loss function. Okay, so you're trying to fit the score to that predicted score using the variables, and you're taking this difference of the two, squaring it, and taking the sum of squares. So this is called the least square fit, Gaussian least square fit. It's solvable in a few seconds given a few million rank reviews, even on your laptop. Okay, and formally it's just finding a hyperplane. All right. So just to illustrate this method, I asked my students to actually run this model, this Gaussian least square fit, and find the values of the various words. And so he came up with these values, as 0.1, good as 0.6. So good is a positive word, right? Loved as 1.1, etc. And so after this Gaussian least square fit has been done, you get these numbers for each word. And now if the machine has to give a score to some new review like this, it just looks up these scalar values for each word and adds them up for the review. Okay, and maybe there's some scaling, but here I'm ignoring the scaling. So that's how this works. Okay, so the machine has learned these scalars, and now it can use it to predict the score for new reviews. And now you look at this, and you realize the discovered patterns in this case are very simple. It's just how these words correlate with a positive score. So loved appears in a lot of positive reviews. So, it has or good, and so those have a higher score. And that can actually be made mathematically precise. So that's what these scores correspond to. But in general, for more complicated models, it's not so easy to understand, what exactly the machine has discovered. So that's an open problem for complicated models. So with that simple model, which was, as I said, sort of the first, by the way, that simple model does predict quite well. It's shockingly good, this naive model. All right, so with that example out of the way, here's the general paradigm in machine learning. That in machine learning, this model fitting that I talked about, or the curve fitting, is really about finding a function which has a desired input-output behavior. And it has some trainable parameters, theta, so it's a vector of parameters. So in the previous example, the input was the movie review written in some kind of data structure, and the output was the score. All right? And so the output of the model was the sum of the theta sub w's of for the words in the review, and that's the output. And the desired output is the score that's assigned by the human. And the training method was to tune these theta sub w's so that the desired output matches as much as possible the true output. Okay, so now more generally, the model may not be this linear model. It could be some different, more general function, f sub theta of x. So it's a function of the model parameters theta and of the input x. And you still have the training data, generally x and y, the input and output. And the loss is defined, again, as some least square fit objective. But this output is now this general function, f sub theta of x. By the way, there are many other ways to formulate the loss, which I won't talk about today. The least square is just the simplest and most classical method. So that's it. So that's what machine learning does today. And I must say that the field of artificial intelligence had many other routes along the way before it arrived at this paradigm, but this is a dominant paradigm today. So mathematically, how does this work? So remember, yes. Yeah, so the question was, you wanted some experimental details, like with 100,000 variables, how many reviews do you need? So actually, a few thousand reviews is already pretty good. Well, yeah, arguably Amazon and Google, etc., have way more, but yeah, but even with a few thousand reviews, you do pretty well. And with some souping up, which I won't describe in this talk, you can probably get by with like a few dozen reviews and do pretty well.
I see. Okay.
Yeah, with a linear model. Okay. All right, so how does that work? So remember that the goal is that the machine has to learn to fit not just the training samples, but also be able to do well on new samples. So the formal way for analyzing that is inherited from classical statistics, where you assume that these samples are drawn, the identical samples or random independent samples from a probability distribution of movie review and the rating score. Okay, so you're imagining a distribution on all possible movie reviews that will ever be written and how the humans would give them scores. So there's a distribution on those, and that the training data is independent samples from that distribution. Okay, this is somewhat of an unnatural assumption because clearly the set of all movie reviews that will be written depends upon the set of all movies that will be created and who goes to watch them. Okay, and those are not trends we know in advance. Okay, and so that distribution is clearly shifting over time. Okay, so this is a simplifying assumption. All right, so, but you're given some samples from that and you fit a model to that. So you optimize the loss function, that's the training. And now testing, you have to take new movie reviews and come up with a prediction for the score for that and see how well it matches the human rating. Well, how does that work? In practice, well, you just take your data and train using 80% of the data and test by evaluating the loss on the remaining 20%. Okay, so since the 20% held out data was never looked at during the training, you can mathematically show that your performance on that held out data is predictive of your performance on unseen reviews that you'll see later. Okay, so I won't go into the math of that, but it's fairly straightforward. Okay, so how does this training work? And the training algorithm is actually fairly simple. So if you're a mathematician, you would look at this, yes? Yes. Yeah, so let's not worry about it. Yeah, the Gaussian assumption is that the difference between the model's output and the true output has a Gaussian distribution. The error, yeah, that's where it comes from. Then it's the correct estimate. Yeah. Just call it least square fit. And then that also makes sense. Okay, so...
more factor. So, and we want to include that factor. So, will it affect the training which has already been done?
Yeah. So the question is, what if... So by factor here, you mean, in this case, just the words. There's a parameter for each word. So now if your vocabulary expands, which happens all the time, languages get new words. Yes, so we don't have a scalar for those words. And so there are all kinds of ways people have invented to deal with that, but I won't talk about that today. Yeah.
So the training and the testing proportion needs to be always around like 80-20.
No, I was, 80-20 is just arbitrary.
So what would be your recommendation, like usually?
It depends on the setting, yeah. So, I mean, all of these splits are also, I mean, there is some black art to it, yeah. It's called hyperparameter search. Yeah, so you actually also have a validation set where you have to tune the model parameters and you reserve some for that, etc. Yeah, the full experimental setup I haven't described so well. Yeah.
Why are we squaring the loss function when we could just do the absolute of it?
You could, yeah, as I said, many other laws. Yeah, what you suggest is what's called the L1 loss.
But most of the time we just square the loss function instead.
No, there's all kinds of losses. I wouldn't even say that that's the most popular these days.
Okay.
Yeah.
See, now we mostly doing here is fitting. It is why we call it learning. Learning is something which is something new.
Good. So yeah, hold that thought.
It is fitting itself.
Yeah. So I mean, this is only like my 10th slide or something. Yeah. Hold that thought. We'll get to it. Okay. So any other questions? Okay. So yeah, if you were a mathematician and you want to learn a function, you would think of, can I come back to that? Maybe the next pause. So you would want to learn a function. There are other techniques you would gravitate towards. For instance, Fourier analysis would be a way to learn an unknown function from data. But those classical methods run in exponential time. Exponential in the number of parameters. And here the number of parameters may be hundreds of thousands or millions or billions, and you really cannot run in exponential time. So the method that's used in machine learning, by and large, is some variant of gradient descent, which is another thing that you learned about, I think, in high school or maybe freshman calculus. So there's some loss function L of theta. At this point, don't worry about what that loss was, just so long as it's differentiable and has a gradient. So remember, gradient is the vector of first derivatives for the function. So the gradient is the direction of where the function changes most rapidly at that point. So negative gradient is the direction where it decreases most rapidly. So gradient descent just consists of starting at some arbitrary point. In practice, it's a random point, a random theta, and then you move a little bit in the direction of negative gradient. And the amount you move is given by this scalar eta, which is called the learning rate. And setting the learning rate is also an art. Now, that's gradient descent. That's, as the picture suggests, you're just descending along, the way water would flow down the slope. And it's surprising that this is such a useful and powerful algorithm in machine learning, because often this loss, in the most interesting cases, is non-convex. So convex means something like this, which has just one valley. And here, of course, a drop of water or a ball rolling down the slope would just find the optimum point. the lowest point. But with a non-convex function, it's not clear at all that if you start here, there's no reason gradient descent will get there because there are all these peaks in between. So a priori, it doesn't look like a very good idea, but in practice, it works really well. And this is one of the mysteries that theory and mathematics are trying to investigate. The other thing I want to mention is that gradient descent is sort of the basic idea, but in practice, people soup it up with various tricks, some of which are you vary this eta, the learning rate, the step size, over time. That's a black art in many settings. You use you maintain the past gradients, not just the current gradient, but also gradients at previous steps. That helps. It's called momentum. There's something called regularization. There are many, many other tricks, which I won't talk about. Okay, so machine learning conferences are filled with papers that continue to invent new tricks, but the basic idea is gradient descent. So with that out of the way, the famous deep learning, what is that? Well, as the name deep suggests, it's a multi-layered model. So multi-layered meaning it alternates between applying a transformation, which is multiplication by matrix, and a nonlinearity. So the input comes in, so it's a multi-layered model. Input comes in, x. First step is a multiplication by matrix vector multiplication. That's a linear transformation. You get m1 times x1. Then you apply this nonlinearity. And the nonlinearity, the simplest nonlinearity used is, given a vector, just zero out all its negative coordinates. Okay, that's called the ReLU nonlinearity. So you apply that, and now then you apply another linear transformation, another multiplication by matrix, then the same nonlinearity, multiplication by matrix, etc. You can do many layers of this. This is called the net. Okay, this is again highly simplistic. You can have features in the deep net such as convolution, bias, skip connections, other loss functions, etc. But that's the basic idea. So that's this nonlinear model, this nonlinear multi-stage model, outputs something, f sub theta of x1. Theta is now these matrices. These are the parameters, the entries of those matrices. And so this model produces an output that depends on these matrices and the input x. That's denoted by f sub theta of x1. And you want it to fit the desired output. And you could, again, fit it using, we discussed before, or some other loss function. So how does this get trained? So again, just to illustrate, you're going to use gradient descent. So you want the gradient of this complicated function, this loss function, with respect to the parameters theta, namely these matrices, the entries of the matrices, those are the parameters. And you want to compute the gradient of the loss. How do you do that? Well, this function is a multi-layered function. It's a composition of functions. So you have to use the chain rule of calculus to compute the gradient. So you do that. And if you want to do it in a naive way, it would be quadratic time. That's too much. If the number of parameters is millions or billions, quadratic time is too much. But the backpropagation algorithm does it in linear time. It's kind of like, from your computer science course, you might remember the difference between bubble sort and quick sort. Okay, so it's just much faster, and it's the workhorse of machine learning. So this, in a nutshell, is machine learning. And I'm happy to take more questions. I believe one more thing I want to say. Yeah, this, of course, is the model. This multi-layered model is the reason for most recent successes and the tech boom. And why does it work? It's nonlinear enough to express many things. So, machine translation, image recognition, etc. And at the same time, it's linear enough, right? You look at it, it's kind of linear enough to allow quick optimization on today's computers. So that's why this has been so successful, it seems. So summary so far, machine learning involves finding patterns in data. Finding patterns is some kind of surface fitting involving millions of variables. Why did it take off in the past decade? The answer is that it's some virtuous triangle of data, commercial payoff, and algorithms and hardware. So this optimization algorithms have been tuned, mostly in an empirical direction, but also theoretical direction over the past couple of decades. There's been new hardware, what's called GPUs, graphical processing units, which are basically supercomputer on a chip. It costs a few hundred to a few $1,000s. It was invented to render graphics for computer games. So realistic graphics for computer games, so they can do a lot of operations in parallel. At some point, computer scientists and machine learning people realize, hey, that's a lot of compute power on a chip. Actually, it's not a chip, it's a board. And you can just plug it into your workstation, many of them, and do a lot of computation in parallel. And so that was very important. And once it took off, of course, companies start using this. And companies are interested in commercial payoff. So in order to get commercial payoff, you're willing to gather more data, large data sets, and which in turn can be used to produce better results and better payoff, and it's all a virtuous cycle. Okay, yeah, question.
So, you said the parameters are the entries of the matrices, but otherwise, matrices are just any. And do you put some?
Yeah, they're structured. That's the convolution that I alluded to.
You'll talk about. But okay, that's one thing. But why don't you put, say, parameters in the nonlinearity?
You do that too. That's called the biases. Yeah.
Okay, and but then this whole setup, I understand that it might be easy to implement. The one you had on your previous slide. It might be easy, it captures some nonlinearity, and then there's the linear part. But at some level, I could imagine many other possibilities.
Yes.
Is there something why this layering is very natural for this? Or you'll say more about?
There's no theory for it. No, layering is natural. Yeah, that seems quite intuitive. That more layers should help. Like even in the human visual cortex, there are 6 to 8 layers.
Right,
but to recognize
layering in this fashion.
In this fashion, it's not clear at all. Yeah, neural nets has been around for 60, 70 years, and people tried all kinds of architectures, and it's kind of surprising and even shocking that the simplest one works very well. And it may well be that this is easier to optimize. So what I said, it's linear enough, close to linear, that it optimizes much better. And so we can train it at very large scale. And the other architectures just get bogged down. But this is guesswork. Yes. Yes. So the question was, while learning the architecture doesn't change. That's basically true. But at the research level, yeah, architecture is also up for grabs, and there's new architectures being invented every year, which I'm not discussing here. Yeah, but for a particular setup, once you've decided you're going to use a certain architecture, yeah, you wouldn't change it. But even so, there are various what are called hyperparameters in the architecture, layer sizes and various other choices, which have to be tuned in practice. Yes. Yeah, go ahead.
I just wanted to ask about, the possibility of overfitting. You said
good, yeah, hold that thought. Yeah, overfitting, I will address, yeah. Okay.
Gauss function is always often non-convex.
Yes. Yeah, basically.
But the square function, the absolute.
It's not because of the square. It's because of the non-linearity. Oh, and also the multilayer.
No, won't the convex function have advantage that it has a minima, global minima? Yeah. So why non-convex? Is there any reason?
Yeah, the convex methods just don't work very well on the complicated tasks. Yeah.
Is there any reason that as an index of x you put the 1 below?
Oh, sorry, no, just typo. It should be x, yeah, sorry.
Okay.
Excuse me?
No, the input is a vector, x1.
Okay.
And the matrices are the parameters of the
So
model.
input is a vector and you output a vector. So can you train like the output vector on any other different neural net and then you like train it, like make it to learn other things too? Can you make one thing to learn everything?
Yeah, so, multiple tasks is what you're talking about. Yeah, so I won't talk about that today here, yeah. Maybe in the last lecture, the third lecture, there'll be some discussion of that. Yeah.
Hyperparameter tuning like a real dark art, like you use only intuition to do it, or is there a formula behind it, or we are still researching for one?
All of those, yeah. So it is a dark art. There's people trying to develop more systematic theory for it. Because ultimately, hyperparameters are also just parameters. And they just happen to be the ones you fix first and then the rest. So they are sort of trained with similar ideas.
Thank you.
Yes.
Each words are provided with scores. That's what you told at the beginning.
Yeah, but now we are sort of in a more general setting, yes.
Yeah. How are these scores provided? Are they manually provided or?
Those are learned by the model.
Learned by the model.
Yes. That's what the least square fit does. So you're talking about. So notice that we've moved past, yeah. So those scores, this training method is going to figure out the theta sub W's.
So the input for this model would be the words or the numerical
review and the score.
Okay.
The numerical score. And it's going to solve this minimization problem. But yeah, in general, these parameters in the deep net, the parameters are these matrices. And those are going to be learned. Yeah.
Mostly classical methods saying Fourier, and those are mostly linear. And they are understandable. Why there is some issue?
Well, they're linear if you go to some exponential size space, yes.
Okay. But with this complex methods where there is non-convex curves, and again it becomes quite not understandable as well.
It's not.
Although you said that it is linear enough.
Okay, but the reason why these work better than anything else is that the training time is generally, in practice, proportional to the number of parameters.
Okay.
Not exponential in the number of parameters.
All right. So that is why this comes ahead. That's fine.
Just in practice. Nobody can prove that.
Okay.
Currently, for complicated models.
Yes.
That in 100n time, where n is the number of parameters, you're done.
Right.
Nobody can prove such a result, but in practice, yes.
We won't be able to know that why these parameters are behaving, or because it becomes non-understandable, even though it is said that...
It's non-understandable, correct, yes. So what these matrices represent, nobody understands.
Okay.
Yeah, this whole sequence of matrices is somehow able to understand images and label them, but what their matrices mean, nobody knows.
Hi, I have so I'm thinking about how does it deal with the problem of induction? So to give an example, people are using to classify galaxies in the new galaxy service. So there will be billions of galaxies, their images will be imported. Then we are classifying them into metal rich, metal poor, or irregular elliptic galaxies, something like that. So if we see, let's say, thousands of galaxies which are very metal poor, so by design, since it's a curve fitting, it will see that these are the out things. But by the design of science, we want to deal with that.
Okay, so this is again the philosophical question. I will get to these, yes.
Okay, thanks.
Okay. And to some extent, also the later talks will deal with some of these more. So, okay, so I'll go on to machine learning in action a little bit. And again, if it wasn't clear already, the exposition is going to be even more simplistic. Ahead. So first thing, so you show this to undergrads, and one thing they comment on, and probably many of you have this question as well, is that, so for the simple linear model, the review rating was a total sentiment score of all words in it, maybe scaled. This is clearly not how we humans do it. Word order in text matters. right? No good is different from good no. So that's one thing, right? So word order matters, whereas if you just add up the scores, that's doesn't depend on the order. But more importantly, you don't need millions of examples or even thousands of examples to learn how to rate movie reviews, right? Remember the first time in your life that you saw a movie review on Amazon or wherever, right? You could assign a score to it, right? You understand the language. You can have a pretty good idea of what this numerical score should be. So you don't need lots of examples. Somehow I can explain to you the task and you can just do it, right? Because you understand language. So that's still an open question, like how to have this kind of flexible intelligence that humans have. But let's talk about this understanding of language. And even here, science has tried for millennia to formalize and understand language. So the logic of the ancient Greeks, and since then, mathematical logic, grammars, either grammar you learned in school, nouns, verbs, etc., or more formal mathematical grammars, model theory. And people did try to do machine learning using some of those ideas, but today, as I said, the paradigm has shifted. And so the question is, how can machines understand language? And arguably, that would be more general purpose in rating reviews. Okay, so this is what's called unsupervised learning. And here, the machine is not going to be given humanly labeled examples. It's just going to use a ton of data. And the data, in this case, is a large corpus of text, like Wikipedia, which has a few tens of billions of words. It's very long. It's more than all of us put together could read in a lifetime. And using this large corpus, you train a model to predict part of the text from the adjacent text. Example, I went to a cafe and ordered A, and reasonable suggestions would be coffee or samosa or pastry, but not a puppy. So a model is going to learn to do such completions by training on huge amounts of text. And clearly, if the model succeeds, then in the process, it must implicitly have picked up on grammar rules, right? That the next word should be a noun, or common sense, that you don't buy a puppy at a cafe. Okay. So as you can imagine, these kinds of models are used in machine translation, question answering, etc. And there's been a lot of progress. And so what I'll describe is a very simple, elementary idea that's used in these more advanced things. So this language model is a baby version of something called word2vec, which was very influential. And this model has some parameters. And the parameters here, remember in the simple linear model, there was a number for every word in the English language. In this model, there's going to be a vector, 300-dimensional vector for each word. And this vector captures the meaning of the word. Why 300? No special reason. It's just sort of large enough to capture interesting aspects of meaning. And this model is trained on the following task. Given the preceding 5 words, W1 through W5, it has to output a distribution on all English words such that it has a good probability of predicting the actual next word. So that may look a little funny, distribution on all English words. How does it output that? Well, we're used to such models, right? A model outputting a distribution, namely a weather prediction model, right? Which also outputs a distribution on outcomes. So in this case, the simple model, outputs the following distribution. The probability of a given word W being output after W1 through W5 is proportional to the exponential of the average inner product between this word W and the preceding 5 words. So the preceding 5 words are the context. And now that context having been set, the probability of the next word being W, a specific word W, is proportional to this. Okay, and this constant of proportionality is called the partition function. There's a normalizing term to make this all a distribution, which I'm ignoring for simplicity. Okay, so given the last 5 words, such a model, if it has these vectors VW, the semantic vectors, will have it will define some kind of a probability distribution for all the 100,000 English words, and it'll give a high probability, hopefully, to coffee or croissant or samosa, and low probability to puppy. So now the question is, how do we train such a model? What's the loss function? And to define the loss function, we should understand what does it mean that such a probabilistic model is fitting the data. And to understand that, realize that even for the simple case of weather prediction, suppose the model says 80% chance of rain tomorrow, and it doesn't rain. Was the prediction wrong? We don't know, right? Because it's at 80%, so there was a 20% chance it would not rain. And it's only after a long period of time you observe it and see how often it actually the predicted events happen with the right probability that you understand whether the model is correct, right? So in this case, the measure of goodness of fit is the following: the reciprocal. So this is a loss function. The reciprocal of the probability assigned by the model to all of Wikipedia. So what does that mean? So after the model has learned the semantic vectors, right, it's theta, what is the probability it assigns to Wikipedia? Now, that can be factored as follows. Take the first 5 words and see the probability assigned to the 6th word. Take the next 5 words and the probability assigned to the 7th word, etc., right? So by Bayes' rule, you can factor it like that. So for each of the billion or 10 billion words in Wikipedia, the probability that the model assigns to it given the last 5 words. And now because of the functional form of the distribution, that can be written in a nice way as, because, product of exponentials is, just like exponential of the sum of the exponents. So you get this nice expression, which is differentiable. Okay, so you minimize this loss function, and how do you do that? Again, by gradient descent. Start with some random values for these vectors, and then use gradient descent to improve these vectors to improve this loss. Sorry? The actual data is Wikipedia. So Wikipedia is a long string of text, and this model, every time it sees 5 words, is predicting a distribution on the next word. And you're trying to maximize the probability it actually assigns to the actual word that appears. And it's a reciprocal of that. Yeah, maybe that was your confusion. Okay. So you train the model and it begins to understand words and predict well. So these semantic word vectors that it learns, the vectors for each word, turn out to have nice, understandable properties. So for example, the cosine of the angle between the vectors captures human estimates of similarity. So the model was not trained with any kind of human knowledge, except Wikipedia. But you ask humans, what's the similarity between lion and tiger? And they might say 0.9 on a 0 to 1 scale. And indeed, the cosine of the angle will be somewhat like that. And tiger and coffee are very different, and the cosine of the angle will be pretty small. So somehow the model's vectors are somehow capturing some human notions of meanings of words. There are all kinds of other magical properties of semantic word vectors, which I'll maybe talk about a little bit in the 3rd lecture. It's also possible to use word vectors to define sentence and paragraph vectors that capture sentence and paragraph similarity. So you take a paragraph of text, 2 paragraphs of text, and ask humans to rate their similarity, and somehow these paragraph vectors, their inner products capture that. Yeah, all of this technology is being used, yes. This is, I'm giving a very baby version of all this, yes. Yeah, you can use semantic vectors to improve the movie rating task, which was asked earlier. You can do it with very few samples. One recent intriguing discovery is that word vector space for different languages, for example, English and French, can be meaningfully aligned via linear transformation. So that, let's say if it was English and Hindi, so man would map to admi approximately, and woman to aurat, and so on. So that's a kind of intriguing discovery which has caused a lot of excitement in machine translation. And I just want to put a footnote there that we'll be using this later in the talk, okay, these paragraph embeddings. Okay, so that's how, yes?
You said earlier that 300 was maybe large enough to capture the space.
Yeah.
Is that something empirical again? Is that less, let's say 20 would not be enough and few thousand is just an overkill?
Yeah, so a few thousand can actually be bad. If it's too,
I see.
The dimension is too high, there's this overfitting kind of issue, yeah.
So this is what works for 100,000 vocabularies of 100,000 words. 300 is roughly a ballpark.
Yeah, but again, this is provisional because you change the model and maybe you'll get rid of the overfitting or change the training method. Yeah, so actually the new models, I think, are somewhat higher dimensional than 300.
So it would clearly depend on the vocabulary. I mean, like 100,000 words.
Also the training method. The training method may avoid overfitting, and then somehow the more dimensions are used meaningfully. Let me move on, if it's okay, because I think I'm running out of time. I'll do the remaining few slides, and then I'll take all your questions. So let me just introduce one more idea, which is, the students say, okay, you can passively understand word meaning, etc. And people are asking this, but how can machines actively interact with the world via a sequence of intelligent decisions? That's a little bit closer to what we think of as intelligence. And here there are 20th century antecedents, like probability theory, betting games, gambling games, etc. Economics, you have to make decisions over many time steps. Control theory, where you are managing the power of a big power plant, and there's also decisions made at every time step for a long period. So all of these antecedents fit into this sequential decision-making framework that I'll talk about now. And for simplicity, I'll use it in the context of game playing, okay, just for illustration. Okay, so an essential feature of sequential decision-making is that you're going to take, as the name suggests, a sequence of decisions over a long period. So, and then the environment will respond as well. So it's a stochastic game in some sense, or your opponent will respond. And so there's in your head, a tree of all possible interactions, okay? All possible scenarios that will play out, that could play out. So now, in our game playing setting, let's say, after all the scenarios are played out, at the end, somebody wins or loses. So a payoff of one, a loss of one is that you lost, and 0 is win. And so what's the way to play the game? At the first step, you want to make a move so that over the rest of the tree, after the first step, you minimize your expected loss. Okay, so this is the classical setting of sequential decision-making from the 20th century. Now, the practical difficulty, so it's fine to just define it that way, but of course, computation is another matter. The tree is just too large to allow full evaluation. I think most of you are familiar with exponential growth, and yeah, if you have depth D, you have exponential in the number of branches, and you cannot do a full evaluation. So most of us have some sense of chess playing software, and the 1990s version of chess playing software, which already was the world champion, involved a list of handcrafted rules which prune this search through the tree. So some moves just don't make sense according to these handcrafted rules. You don't give up your queen, etc., etc. And so you have some handcrafted rules, and you combine that with some clever move evaluation algorithm, which takes probabilities over how the tree would develop. Okay, so that was the classical framework from 1990s. But as I said, today, the paradigm is learning from data. So no handcrafted rules. Unlike the old examples, we're not going to have 10 grandmasters come in and design the program for us. So no handcrafted rules. So if no handcrafted rules, what should we have instead? A model, which will learn from just data, in this case from self-play. We'll still have a move evaluation algorithm, although in the advanced version of this, even the move evaluation algorithm is a model. Okay, so how does this all work? So the input to the model is the current board position and how many moves have passed in some suitable data structure. And the output is a distribution on moves of the next move. And it's trying to decide, it's trying to tune the model parameters so that this distribution on moves is a good strategy. So of course, the same model is going to be applied throughout the game tree at all the future steps. So you can do a tree evaluation using the same model. You can train a model for white and black if you like. And so using the move evaluation algorithm, kind of like from the 1990s, you can evaluate, get an estimate of the loss, the probability of losing the game, given that your current model parameters are theta. Okay, so at any point in the tree, you can evaluate the expected loss, the probability that you'll lose. Okay? But now remember that to train a model, we use gradient descent. So we want an estimate of the gradient with respect to theta. Okay, so we can only evaluate the loss probability. We don't have the gradient. But if you think about it for a second, or for a few minutes, you'll realize, well, you can do a crude method to evaluate the gradient, namely, take a bunch of random vectors eta, and now, by Taylor expansion, the loss of theta plus eta is a small noise vector, is approximately L of theta plus the noise vector in a product with the gradient. So if you do it for enough noise vectors eta, you can, by solving a system of linear equations, estimate the gradient. So this is a very crude method. People use more sophisticated methods to estimate the gradient, but that gives you the idea. Okay, so by just doing a few move evaluations and solving a system of equations, you can find an estimate for the gradient. So that's the way it works. Okay, so you're using a model to play the moves and training it by the same kind of procedure. Okay, so there's no human grandmasters training it. It's just going to learn to play chess or Go by playing itself, or the same kind of model, and doing the move evaluation and doing gradient updates. And with the new versions of chess and Go that have come up here, the models are really coming up with amazing new moves, which completely floor the human experts. Okay, so I'm a little short of time. I'll just race through the rest of the slides and then answer questions. So mathematical understanding of deep learning. This is also the topic of the next talk, so I won't say too much here, but some key questions. When, why does gradient descent work, and how fast? Why deep and not shallow? How does depth help? Why doesn't training overfit to training data? So, okay. Yeah, but I do have a few minutes still here. So why doesn't training overfit to training data? So number of parameters in these models is way more than the number of training examples. Okay, and there's so many parameters that the current models are even capable of achieving zero loss on random data generated by a random number generator. So some of these models have a lot of parameters lying around, but when you train them on real data, they don't overfit. And to illustrate the overfitting example, let's go back to this simple unemployment and unemployment data. And instead of, if you have too many parameters, the model can do this crazy fit to the data, which works well on the training data, but then it won't predict well on the new data. So that's called overfitting. And deep models are definitely capable of doing this kind of overfitting, as shown by these experimental results, but with proper data, they don't overfit. So that's a mystery. How to interpret the trained models' inner workings? That's another open question, and that actually is largely no theory still. So analysis of optimization. The main problem for theory and mathematics here is that this loss function is essentially a black box to us. So now you might be saying, wait, why is it a black box? I mean, you're given this explicit formula for it. And the reason it's a black box for mathematics is that we don't have a mathematical description of X, Y pairs. You know, what makes a bunch of pixels an image of a doll? We don't have any mathematical description for it, and the only description we do have involves deep nets that are experimentally derived. So really, it's hard to have a theorem saying, you know, for this kind of data, the training works, because we don't have a mathematical formulation of what the data is. Okay, so that's the issue. And so, you know, there's various ways around it. There's a black box analysis, which I'll talk about more in the next talk. So there's more about optimization next talk, including recent works using trajectory analysis of gradient descent. Okay, so it seems that this gradient descent algorithm, which seems so naive, actually is doing something very smart. And we don't exactly understand it, but basically the landscape of the loss can be very complicated in general. If you try to do math with the entire landscape, it's very difficult. But somehow gradient descent seems to pick out interesting trajectories. And analyzing those trajectories of gradient descent is a very fertile area right now. Why no overfitting? You can even today train models with 20 million parameters with 50,000 examples, for example. And a popular conjecture is that when trained on realistic data, the net's parameters are constrained either by the problem or the data or by the training to be highly interdependent. So that they're not really 20 million parameters, but much fewer. And the way it's often phrased informally is that the set of viable parameters lies on some manifold. And so the next talk will give a partial realization of the suggestion. And basically, we are looking at, I mean, we and other teams are looking at trained networks, big, deep networks. And in our paper, we identified a certain noise stability property of networks, using which we can prove a theorem showing that this noise stability property implies that their parameters lie on a lower dimensional subspace of the trained net. So that's a partial realization of this conjecture. So taking stock and wrapping up. So I think this came up earlier in a question. Look, this is all mindless model fitting. Where's the learning in this? And to some extent, this is a problem with all technology, right? That once you understand how it works, some of the mystery lifts, right? But more seriously, people say, okay, this is not remotely how humans think. So some answers to that. Well, the imitation approach has not worked well in the past, right? Until 100 years ago, the only things that flew were things that flapped their wings. And that turns out not to be the best way to have machines fly, because we have things like propellers and jet engines, which are way more powerful than flapping wings. But it's a different kind of flight. So it's understood. It's very powerful, but it's different. And I think that may be a feature of machine learning for the foreseeable future, that it's different kind of intelligence, incomparable to humans, but still very useful. And in fact, the machine's advantage lies precisely in the ability to crunch data. Just as the flying machines leverage jet engines, thinking machines leverage lots of data. Why? Because they can crunch it, and we cannot. We humans cannot. And finally, and most seriously, it's fine and good to say, hey, design machines that, act like humans. The hurdle is that at an operational level, we have very little idea how humans think. In fact, arguably, machine learning is currently the best hope for figuring out how humans think. So I'll describe here a simple, interesting experimental work that we were involved in with our neuroscience colleagues at Princeton. And the paper appeared last year, actually 2017, which is analysis of fMRI data. fMRI is a scanner where a person, which is one of the few techniques which can get some kind of image of the brain working while the subject is awake and alert. So the subject is in the scanner and watching, in this case, Sherlock Holmes movie. And the fMRI machine is taking measurements of the blood flow at 50,000 points in the brain. Instantaneous blood flow. And it does it every few seconds. So therefore, for every time step, the scanner gives you a voxel vector, which is a 50,000 dimensional vector of blood flow measurements. So now, to show that you understand human thinking at some level, you have to somehow come up with some description of how this fMRI, the blood flow response vector, corresponds to the signal that was being presented, the movie. I must admit that when I first heard about fMRI some years ago, I thought this was crazy. You know, blood flow measurements. I mean, what are we talking about here? Civil engineering? You know, fluid mechanics? So, but then you realize that actually it makes sense because we know that the brain actually has hundreds of different regions, probably more. And they are doing different things. And so blood flow measurements are measuring activity in these different regions, and it's some kind of a snapshot of your emotional response to the movie. So how do you measure your understanding of the voxel vector? Well, one task you could try to do is to pair them up with the movie scene. So in this case, because the movie stimulus is very complicated, right? Explosions, dialogue, video, it's complicated. So my colleagues came up with the idea of giving a text annotation to every few seconds of the movie. So something like Sherlock and John are talking about the murder in an old room with Mrs. Hudson. So it's a description of a few seconds. Okay, so now you have text descriptions for those few seconds and the voxel vector for that few seconds. And now, to show that you understand the mapping between the two, you could try to solve, or have the machine solve, the following set of tasks. Like you take 5 time steps, and you take the corresponding text descriptors, the text descriptions, and the corresponding voxel vectors, and now you permute these, and ask the machine, you know, which one corresponds to which, right? Do the matching task. Okay, so if you can do the matching task, you can now say, okay, I sort of understand this mapping, and then you can sort of look at, you know, which voxels were active and get some idea of where the brain is active, etc. So it turns out you can do that. And how do you do that? By the way, this is not your typical applied math problem the mathematicians here may have seen, because there's no mathematical model for human language. Right? Those simple applied math situations like signal processing you've seen, there's a mathematical model. Here, there's no mathematical model. So to provide the mathematical model, we designed these semantic embeddings of text that I alluded to earlier, especially for this project. And so you can replace the text annotation with a vector, an embedding of the paragraph, and then we use the mapping using that, and you can get a success rate of something like 80–90% in predicting, matching them up. Okay. Yes. So what did my colleagues, the neuroscience colleagues, were looking for? So once you learn, what this mapping is using, you start seeing what are the important areas. So you can try to see, like if I take a subset of those 50,000 voxels, based on some neuroscience information, can I do the prediction as well? And then you can sort of see, okay, those are the areas of the brain that are following the movie. So those are the kinds of pictures which I wouldn't be able to, I've forgotten the names of some of these areas. They're like dozens or hundreds of areas in the brain, and they're tracking the movie. Okay, so the hottest trend in academia is ML plus field X, of course, neuroscience, biology, social science, etc. Okay. It's linked from my homepage, the Vodrahalli et al. Paper. But I want to emphasize there are many people trying to apply machine learning to these fields, okay? I was just giving an example, which sort of tied together other things from earlier in the talk. Okay, so I want to end with this question for this audience. Can machine learning thrive in India? And maybe here's a field where the advances are rapidly being applied to applications, either scientific applications or commercial. And most of these ML advances that I see, also including in the applications, are driven by PhDs. including the tech companies, by armies of PhDs. And that's a question for India. Like, I think the PhD production levels are really low. And worse, these days, it seems to me that the top Indian undergrads don't even seem to go for PhDs. I guess they have other job opportunities elsewhere. And there's a dramatic difference compared to China and also to India in the past, from my time or even 15 years ago. So it's a question for people here. What can be done about it? So concluding thoughts on ML. ML starts with these age-old wonders and mysteries, like what is learning, what does it mean to understand the world? It gives a new way of looking at the world via complicated and inexact descriptions, but maybe those are the best we'll ever have. It is a new frontier for science and math, and I'm optimistic that deep learning methods can be mathematically understood or simplified. Thank you very much.
Thanks very much, Sanjeev. You'll take some more questions.
Yeah. Sure, yeah.
But your chess example, I mean, this AlphaZero, which has created a significant sensation. So one thing that surprised me, and maybe you can shed some light on this, is that in chess, first of all, the number of positions is discrete. And second, it's very hard to define. I mean, I would have naively imagined that the function from position to move isn't continuous because you change one small thing and then the right move changes. And also,
it's continuous in the parameters.
It's continuous in the, okay, so the derivatives are very large somewhere. I mean, it's maybe continuous, but I just meant you change the position a little bit and the correct move to play could be something totally different. So I would be worried that there's huge gradients. And second, that also the cost of...
That just means the Lipschitz constant is large, yeah.
That's right.
Yeah, which a deep net can easily have.
I see. But the other thing I want to say is also the cost of inaccuracy is really high. You're not allowed to make an inaccurate move anywhere along the way. So I was surprised that this is the kind of thing that, as opposed to scoring movie reviews and so on.
When you see it, it feels like this cannot work, but it works. Yeah, I don't have any other explanation. Yeah, people are trying to understand more, but right now that's the best we can do.
Yeah, hi.
By the way, maybe what's going on is that, these, I don't know how big the AlphaGo net is, but, certainly millions or tens of millions of parameters, maybe hundreds of millions, I forget. But I think it's just a fundamentally different set of things that can do compared to us. There's some there's some idea that humans only have 1 million concepts in their brain, right? 20 questions or whatever. So, so maybe to just play Go well or chess well, there's just enough patterns it has to recognize, and at some level it can just recognize way more patterns than we can, with a few 100 million parameters, and maybe it's just conceptually a different game altogether. Once you can do that.
Yeah. Hi, I was just wondering, you mentioned most approaches these. Yeah, I was just wondering that you were mentioning most approaches these are data driven, but data these days can be biased, it can be hard to get or something like that. So why don't we actually integrate human knowledge into the picture?
Oh, we do, yeah. I mean, for a production system, a tech company is willing to do everything, right? Yeah. I'm simplifying. Yeah, a production system will do whatever it can to get a commercial advantage. Yeah.
But maybe going back to that chess thing, I think probably it might have hurt AlphaZero to have put in, let's say, the history of all chess games or something like that, which is probably why they didn't do it. Right? I mean, sometimes perhaps it might be counterproductive.
Yeah. So. That was a game in AI for 50 years to put in human knowledge, and somehow that's been swept away, and it seems that just let it learn from data is better.
There was the question up there first.
I had...
Please wait for the mics.
I had a question on the word vectors. You had noted there that it's a linear transformation between different languages. Is it I mean,
very related languages, English and French. Yeah.
Oh, related.
Yeah.
I
English
mean,
and
as it.
Japanese, it's probably not. Yeah.
Oh, okay. I see.
I don't know.
Yeah, word order was sort of built in the sense that the first.
No, that the model can change. Yeah, but yeah, somehow, yeah, Chinese pictograms. You know, it's
Is it also a function of the corpus size between the languages? I mean, should be around the same order, or even if it's English and French,
you have to be able to train the model in both languages separately. Yeah, so you need a big enough corpus.
Okay, thank you.
It's not clear if you need, after a corpus is big enough, I don't know, a few 100 million, maybe 1 billion, it's big enough.
I have one question. In machine learning, is it possible that certain input data or input parameters can exclude it after a certain time if it is unused for
Yes.
a given?
Yeah, so unused parameters. So of course, unused is hard to tell because these are continuous things. But yes, it's a big area. If you actually want to take a deep net and put it into a chip for commercial purposes or whatever, people compress the net. And actually, there'll be some element of that in the next talk as well. Yeah, so you can compress the trained net 100 times often.
What is the difference between...
First him, then...
Okay, you talked a little about the overfitting curve. Okay. So how do we know if it's overfitting or like it's a correct optimistic fit? Like, is it just trial and error, or suppose I use a specific training algorithm? So does it have a optimum range for fitting curves and all?
No, there's no theory because we are sort of in uncharted waters here. You have number of parameters on the model is way more than the number of training samples. So what should make it overfit? There's all kinds of practical heuristics to avoid overfitting. But
so what you do is you just fit it to some like range and you optimize it later with a like optimum number of fit. You optimize it till you get a better fit.
Okay, realize overfitting refers to the held out data. So overfitting technically is the following. You train on training data, and remember there was a 20% held out data. You evaluate on held out data, and it's like completely off. That's called overfitting, that you overfit it to the training data.
And then, yeah.
So in gradient descent, if gradient descent is used in a non-convex loss landscape, it will get stuck inside the closest minima, right? So, and the minima it will get stuck in, that depends on the initialization conditions, where exactly the algorithm is initialized.
Random initialization, yeah.
Yeah, so if it's random initialization, then after optimization is over and done, how do we know that the minima our algorithm has found is the global minima, that there is no better...
It's not a global minimum. So it's close, it has low loss. So, the loss can be 0. That would be the best. It may be 0.1 or whatever. It's low. And yeah. And you go and test it on the held out data, and if it works well, you declare victory.
So we don't try to look for a global minimum.
No. In fact, there's evidence that going for the global minimum is bad because of overfitting.
Hi.
Yes, Penta.
Hello. I didn't quite understand the correlation between the MRI data, which is from an actual human brain sample, and the Sherlock Holmes movie. I mean, can you just go over it again? What do you learn about Sherlock
So the voxels you understood, right? That's blood flow. That's 50,000 dimensional. And the paragraph was, something like this, right? There's an embedding for the paragraph, a 300 dimensional embedding for the paragraph, for every paragraph, which we define. And the advantage of this method was that it didn't use any training data. So here, the amount of training data is very little, right? Like the subject is in the scanner for whatever, small amount of time, 20 minutes or something. And so there's limited amount of training data, right? So you can't define a new language model for this. So we came up with a method, the SIF embedding, and that is a 300 dimensional embedding for text. And that has nothing to do with fMRI or Sherlock or anything. And then we replace that text with that 300 dimensional vector. And now we set up some kind of a mapping between the 50,000 dimensional vector and the 300 dimensional vector.
Yeah, what is the difference between machine learning and deep learning?
Deep learning is a part of machine learning, as I said. It uses this multi-layer model.
See, how come it came on that chess game?
Oh, whenever you're training a model, you have a choice of what kind of model you use, and people are using deep models.
So you have mentioned that using very few examples also we can train the data. Like
in some cases, yes.
In some cases, like can you put light on that? Like any methods, specific methods?
You're talking about the linear model. I mentioned this for the linear model at some point.
Yeah.
Maybe talk to me separately. Yeah.
Okay.
Yeah.
Yeah. In the word-to-vec case, do you lose generalization error by restricting the vectors to lie on a unit sphere? I mean, do the lengths of these vectors mean anything?
Lengths of the vectors do mean things, yeah, and we have various papers about the theory of these vectors, yeah. You don't make them unit vectors, yeah.
Yeah.
Roughly speaking, it's a log probability of the word, occurrence of the word, length.
Yeah. Sanjeev.
Yeah.
In terms of problems that you pick, I think one of the magical parts of this is finding the right problem to solve using this technology. So are there any guidelines you would have in terms of what problems tend to fit well and could give you meaningful set of results?
What doesn't work so far? I mean,
what doesn't work?
We can pick any set of variables and say, is there a correlation between sun rising and me getting a better grade to, reviews?
Okay, so I think where the signal is weak, deep learning so far doesn't work so well. So what you talked about, like the relationship between whatever weather and your salary or something, the signal is very weak. In all these cases, the signal is very strong, right? Like the language thing, like most humans, after seeing the sentence have like 2 or 3 words that could follow it, right? It's a very strong signal out of 100,000. As opposed to, you take a lot of weather data and see if your salary went up or not. It's a very weak signal.
There are a couple of machine learning methods which are working on weak hypothesis.
There's a very big area, yeah. I mean, the machine learning conference these days is held in a convention center and there are 10,000 people. And the registration for the 10,000 spots sells out in 11 minutes or something. So it's a big area with lots of things going on. Yeah. So this is a very basic introduction to.
So I have a few questions, actually, more than one. The first one goes back to the question on the 300 dimensions. So effectively, I find, on the one hand, we are talking about millions and billions of variables, but perhaps it is those 300 dimensions.
300 per word.
Sorry?
300 per word. Is that what
okay. But in the end, the magnitude of that 300 is kind of the same for all the
you mean in the
different
Sherlock
words.
Example. In the Sherlock example.
Yeah, my point was that even though we are having millions of variables, in the end, it's those 300 dimensions that are explaining, right, its behavior.
Very weak correlation. I don't call it, this is like.
Because I relate that to a very classic heuristic which was present among statisticians who were doing regression modeling, which was saying that to explain a phenomena, they were often taking a heuristic of 10, right? That used to match. So, I
don't believe that. It's just they were limited by data and algorithms and whatever.
Yeah,
Notice that here, the number of parameters is way more. The mapping between 50,000 and 300 dimensional. Yeah. Has way more parameters.
But definitely, don't you think that
representing the brain state in some sense, right? This semantic signal with 300 dimensions. Right. And indeed, these 50,000 also can be compressed to, I forget what it was, 1,000 or something like that. Dimension.
Right. But in the end, it's a small number of dimensions which end up explaining. It's not an explanation, it's an association.
It's a representation.
Right.
My third lecture is about representation learning. Yes.
Right.
Where we'll also re-encounter text embeddings.
I had a second question, which is, so you have a data set on which you apply a model. A lot of the time when you and this stems from my little experiences of running some models in production, actually. There's a lot of taking care which seems to be needed to guard the assumptions under which machine learning models, this IID assumptions. And so could you throw a little bit of light on what actually we could do to safeguard the sanctity of the model that's there and be able to, so that what we can do about that? Or can machine learning itself integrate some of those factors?
Yes. So the IID model assumption.
Yeah.
I mean, when I introduced it, I already said, yeah, it's a philosophical assumption which really doesn't capture reality so well. And that really comes to bite you, because clearly human intelligence, like a kid grows up in the Sahara Desert, only saw sand, right? And can go to the Amazon jungle or Greenland with snow and still sort of operate okay. So clearly human intelligence and general intelligence should be much more flexible. And this assumption that the held out data or the future data is just like the data you saw is not correct. And there are branches of machine learning trying to address that, including some that I'll talk about in the third lecture. But it's still a very baby.
And I had a last question. It's really, really quick one. So in the optimization formulation that we have, do we ever investigate that when a certain variable changes? In normal optimization, you can do robust optimization, which is basically allowing that the final objective function's value will not differ very much, even if you change some of these the sensitivities of the
so if you are staying on for the second talk, you'll see already the noise stability property.
Okay.
Yeah. But yeah, robust optimization is kind of interesting because also we know that it's just not about the parameters of the model, but if you change the input a little bit, like you take an image, I'll take an image of your face and change a few pixels and the model thinks it's a tree or
It's being used for attacks.
Yeah, so there's...
So last two questions, one over there and one over there.
So you mentioned that human learning might be a bit different because it doesn't require so many learning sets. But in some sense, like we're receiving learning, all the time in maybe related tasks, right? So in that sense, maybe it's we are also exposed to large number of training sets on maybe not exactly the same task, but
my third lecture, very much, yeah. It uses that exactly, yeah.
So the last question.
In this particular example, like this stimulus is very complex, like it has auditory as well as visual stimulus. And like which specifically area of the brain you analyze, like in brain in general whole or like some specific areas? Because it will stimulate the occipital lobe as well as the language areas. So
yeah, so it's been a couple of years since we did the paper, and anyway, I'm not the neuroscience expert here. But I think those were,
it will activate many areas of the brain.
Yeah. And that was exactly what they were trying to figure out. Yeah. Like which areas are following the story, right? Basically, we're just looking at the story here. Which areas are following the story.
Okay, good. Sanjeev will be around, and please do come back for the second lecture. And we'll reconvene at 3 o'clock.